ఇందులో ఎంతమంది అండి ఫ్యాకల్టీ డాక్టర్ రెడ్డి
సార్
ఎంతమంది ఫ్యాకల్టీ అండ్ ఎంతమంది స్టూడెంట్స్?
ఇందులో మేజర్ కాంపోనెంట్ టీచర్స్ తోనే ప్రాక్టీసింగ్ ఇంజనీర్స్ సార్. Totally there are about 290 sir, comprising of faculty members and teachers. So depending upon their convenience, they are attending through Google Meet and YouTube. So final number will come to know only when we consolidate the attendance device.
Okay, yeah. Good morning, Arun. Good morning.
Sir, we'll start at 9:05, sir.
Okay, no problem. Yeah.
Good morning to all of you. I welcome all of you to the forenoon session of 6th day for AICT Quality Improvement Scheme Faculty Development Program on Shallow and Deep Foundations. I hope you are enjoying the sessions and you are finding the lecture content very useful, and it is enabling you to update your knowledge in the area of shallow and deep foundations. So in today's morning session, we'll have a lecture on lateral load capacity of single pile and group of piles. The eminent Professor Madhav sir. So as all of you know, generally geotechnical consultants do not provide detailed calculations for lateral load capacity. After estimating load carrying capacity compression, they simply say, right, lateral load carrying capacity can be taken as 5 to 10%. Some consultants, to account for fixing, they suggest a value of 10 to 15% of load carrying capacity compressed as lateral load capacity. But in reality, the lateral load carrying capacity depends on the surrounding soil, into which pile is surrounding soil that is prevalent around the pile, and whether your pile is socketed or not.
Time కావాలి ఇక్కడ silent లో.
So the lateral load carrying capacity in soils depends on. I request the participants to keep your audio muted. So the lateral load carrying capacity in soils mainly depends on the passive resistance that is coming from soil surrounding the pile. For rock socketed piles, the lateral load carrying capacity comes from what is the socket length you are giving to your pile, particularly in a region like Visakhapatnam, where marine clays are present in port area and all. We go for piles which are socketed into rock. So above rock, whatever soil will be there is very soft clay with very low shear strength, right? So all these issues will be clearly explained by Professor M.R. Madhav sir. I request Professor Madhav sir to deliver his lecture.
Thank you, Professor Reddy. Very
Sir, your audio is muted, sir. Sir, slide is visible, but your audio is muted, sir.
now.
Now okay, sir.
Okay. Okay. Now both are okay, audio and the screen.
Yes, sir.
Okay. Thank you, Professor Reddy, for that nice introduction. Very nice morning to all the participants. It will be my pleasure to share with you some issues with regard to lateral loaded piles, both the design and analysis. As Professor Reddy just now mentioned, most of the people don't take lateral load capacity very seriously, but in some of the major projects I found the controlling aspect is the lateral load and not the axial load. And the other interesting thing is now we are using these piles not only to take the structural load from the superstructure, but also we are using these piles to take the load from the moving soil. As you can see in some of the present slides, we will see that piles can be loaded by structural load from top or from the soil movement, which is being attempted to be prevented. So basically, this is what most of us are aware. You can see that the building heavy structure, we have a tall structure, high-rise building. Quite a bit of it comes from the wind load. And that is, the higher you go, the larger would be the lateral load, and that will lead to both moments and lateral forces too. And the pile is supposed to take care of that. Then all the jetty structures you can see, the ship parking there or hitting the top will give you a lot of lateral load, the same thing that you see on this side. Then when you have these overhead water tanks, obviously they're top heavy and they're fairly high. Maybe the staging is around 15 to 18, 20 meters. And so you will end up getting a lot of lateral load and moments. So when I say lateral load, actually it includes also the moment because of the same. And the transmission towers are another very important structure now, wherein we have different types. You can have a lattice type, you can have a pole, you have a H frame, or you have the guide tower. Guide tower is slightly safer because the forces are anchored down below, but other structures will have lateral forces from the cables. When you design, if the cables are all in position, there is not much of a problem. But if there is a cable break, which is what you designed for, then the whole pole or the structure will be subjected to large lateral forces and moments. This is a very serious issue in many of these. But the latest, I would say, would be the wind turbines, which are coming up all over, and the height and the size is becoming very, very large. You can see one of them is now, recently they have set it up in 20 to 50 meters of water. The height above the sea level is even about 100 meters. And look at the wingspan, it's again 100 meters, 120. And the wind is acting on the blades. So obviously the forces will be transmitted to the wind turbine pole and then down below into the foundation. And here we have different types of structures you have an inverted type of foundation on the ground level, but in the sea, you need a large group you can't have a gravity kind of structure. So we'll end up getting very large lateral forces and moments. And this will be one of the more interesting latest topics that all of us will have to deal and work with it. And I think I'm full screen, right? I'm sorry, okay. Another type of wind turbine, you can see the components. One is the horizontal axis about which the blades rotate. The second one would be a vertical axis one. And you see the components here. And the scale you can easily see. It's very high, very tall structure, so the wind forces are very large. And this is how the wind turbine heights are increasing over a period of time, and now we are gone into even deep sea, and there we have to end up having piles to take care of the lateral forces. Then once you have these wind turbines in the sea, you also end up getting wave loading. So you end up getting a lot of cyclic loading, which means that you have to go for a large number of cycles and the soil becomes pseudo-elastic and you have to take care of that too. Then piles we are using for a lot of, apart from structural support, excavation support. And recently also we had one particular case somewhere here in Andhra, wherein a deep excavation had to be supported by piles. We couldn't provide nailing, that wasn't adequate because there was an adjacent building and there was no way we could nail it. So we had to put these touch piles and secant piles, they're all provided for the support. And some of the retaining walls are also supported on that, and you see the bridge foundations anyway. These are some of the basement walls that you can see. Some of them are what can jet grouted or cement mix piles. They can be also, particularly for these metro foundations, we are using diaphragm walls too. All of them take care of the lateral forces from the soil, not the structural load. The piles are also being used to support unstable slopes. These are a couple of examples where we provide these piles so that the slope becomes more stable. And particularly one on the right, you can see here, there is a tall structure adjacent to a slope. And this is one particular case. Very similar one is there in Bombay too, in one of the Kambala Hills area, where you had to provide some support so that the building foundations are all safe too. So these are the schematic that wanted to show how some of the piles can increase the stability. You surface here, once you put the piles, obviously you got to shear them, so the shear resistance of the piles and their moment resistance is contributing to stability. This is one case where we had applied to in Himachal Pradesh, where the toe of the slope is likely to creep and fail. So we had to provide some well foundations here so that the failure surface is intercepted and the well foundations anchored into rock are providing the support. Of course, the bridges, abutments are another classic example. You not only have structural load from the bridge, but you have the lateral earth pressures, because of which you will end up getting instability, in which case you have to provide for piles, both in the embankment and below the footing too. So these are various applications. So analysis in terms of slope stability is fairly simple extension of our conventional slope stability analysis. We take a typical trial circle, we know how to analyze, then we had to introduce the forces due to the pile. This part is the challenging part. How much of resistance can the pile offer? So if the soil here is moving, we still do not know how exactly is the loading on the pile will be due to moving soil. There are some theories where we talk in terms of wedge failure, etc. And because of that, you have the resistance coming and the shearing force or force mobilized. These we add to the resisting force and calculate the new factor of safety. Then some of the ground movements associated with excavations. When you have a tunneling and you have a movement here for the structure, one of the best ways would be try to provide sheet piles and do the prevention of the movements there too. So these are the ways in which we try to prevent the, because of the tunneling, we try to prevent the movement affecting the structure. If you don't, this is a kind of crack pattern somebody has simulated using the finite element analysis. In addition to that, we have these earthquake forces. Here is a typical seismic map of India, and you can see that fortunately in the south, Visakhapatnam, etc., they're all in south, they're in zone 2 and zone 3. But if you go to the north, Delhi, Jammu, Kashmir, northeast, of course, is in zone 5. And of course, again, here, Gujarat, Kutch area, zone 5. Here you have very serious problem. Because of earthquakes, we'll have several lateral forces, which we had to design all the buildings and structures. Of late, we are seeing a lot of activity around Delhi, Haryana. And even if there is a major earthquake in Jammu, Kashmir, Nepal, we find the effect right in this part of the country too. So when I try to analyze the piles, I want to start with how to classify that. Because piles are very long, slender members. So we first look at the length as a criterion. You can have a short pile, intermediate length pile, and a long pile. The idea is that a short pile, L by D less than maybe 5 to 10, it acts like a rigid pile. A very infinitely long pile acts like a cantilever, whereas intermediate pile, I need to consider the fixity at the top and bottom. The second type is the restrained. Piles can be restrained at the top as well also at the bottom. We will see how it is being deployed. If I have no pile cap at the top, like a pole, it's a free pile. Whereas if I encase the pile in a pile cap, it becomes restrained. At the bottom also, if I leave it in a deformable solid, it can be free tip. If you just push it into hard rock, then it becomes pinned, it's allowed to rotate. And if you drive much deeper, it can be fixed too. So based on length, how do I do that? We first calculate the parameter beta, which is nothing but lateral subgrade coefficient KH into diameter by 4 times EPIP, the frictional stiffness of the pile material. EP is the modulus of elasticity of the pile material. I is the moment of inertia of the pile material. So you can easily calculate, if you know the property of the soil in terms of KH, beta can be found out. If beta is less than 0.5, you treat this pile as a rigid pile. And if beta is greater than 1.5, or some people give it as 2.5, then it's infinitely long pile. And other cases fall in between, we call them intermediate piles. As I said, restrained, free or fixed head, the top, if it is free to rotate and displace, it's free pile. If it is free to displace but fixed in terms of rotation, we call it fixed head pile. The tip can be free, which means it is free to displace and rotate. Hinged means displacement is 0, but it is free to rotate. Fixed means it is displacement and rotation or fixed. So these are the kind of mechanisms. Based on that, we try to identify what kind of failure is possible. So I want you to look at the possible ones here, and I have a rigid pile here. If you apply load, because it's a short pile, rigid pile, it tries to rotate about a point of rotation, maybe located at some depth h from the top. I want you to visualize the pile is being treated as a rigid one, which means above the point of rotation, the pile will move to the right because the forcing h is towards the right, and below the point of rotation, the pile will move to the left. So you can see the pressures that are mobilized. Maybe the soil is not strong enough, so you end up getting a smaller stress near the surface, and as you go deeper, this will be the one. And so we try to determine the reaction from this soil and put the pressure distribution, we linearize it. In order to solve it, what we say is that instead of taking this transition, the simple mechanism assumes kind of sudden jump to the right and left. So what we have is the reaction from the right and reaction from the left. We sum it up to get the value of h. If you keep on increasing, it is possible that the bending moment will be maximum at some point, in which case it can form a hinge. If it's a long pile and then you have a hinge mechanism, then we say above the hinge it's going to rotate. In which case this will be our pressure distribution, and we try to do the same. So in order to simplify this, this was originally given by Brahms way back in 1964. One thing I would like you to consider later would be, way back in 1964, he was working in Sweden, where the soils near the top were very weak. So he said, let's neglect the 1.5D. We don't need to do that because most of our pile caps are already embedded in. So in my experience, we neglect this, though our code still keeps saying that you have to have 1.5D, you neglect it. And then the moment is large enough that the soil reaction is already fully mobilized. And he suggests taking 9 times Cu. Above the point of rotation, the reaction is from the right. Below the point of rotation, the reaction is from the left. So based on this, you can simply write the equilibrium equation and get the ultimate load. This is how the bending moment diagram will look like. You can see that the bending moment due to load is starting here, and it starts reducing. It's increasing because as you go deeper and the soil reaction is not adequate. At some point, you will find the maximum bending moment, and by the time you go to the tip, which is a free one, the bending moment is 0. And this is where I would say if the bending moment is very large, as you can see here, maximum bending moment, you will get a hinge. And then we start working on the reaction. So if there's a hinge here and the pile is rotating above that as a linear one, you can see the pressure soil reaction is 9 Cu. Again, he neglected 1.5D here, but he says that, and then after that decreases. So it's very easy to write the equilibrium equation, and you can say the force and moment equilibrium, we solve for these two. This is free head pile. If you have the pile embedded in a pile cap, I want you to notice this. Most of the time, this is the most common situation wherein about 300 to 500 mm, the reinforcement from the pile is taken into the pile cap and you cast it. That means the pile is no more free to rotate, but it is allowed to displace. Lateral displacement is allowed. So if I have a force acting here, it will be a rigid body translation, in which case the full soil resistance of 9 Cu is mobilized, and you calculate the force, and you will find that the bending moment obviously is very high or maximum near the ground surface, and as you go to the tip, it becomes 0. Then these are the other mechanisms where you have a relatively large pile, and if this bend of the pile cap reaches the yield moment, the pile will yield and you have a hinge here, in which case the pile is still rotating as a rigid body, and then you will get the second kind of mechanism. If you have very long pile, you may end up getting 2 hinges, one at the pile cap, and as you go deeper, the bending moment on the other side. One is a negative bending moment, as you can see here. The second one is the positive bending moment, and we had to analyze these conditions. This is what I keep telling, that piles are not very simple. You have to look at the restraint at the top and bottom, and also the length. So this is a very simple way of showing it. I have a short pile encased, so you can see simple translation. Then as the length increases and the stiffness of bending moment it becomes large, you get the first hinge. Go further, much longer, then you will end up getting 2 hinges for the lateral capacity. The same thing in case of sands too, what we have seen earlier, where we had found out the ultimate lateral resistance is 9 times Cu undrained strength of the soil. Whereas in case of piles, we go for the passive concept. The pile is moving to the right, so you'll get the passive pressure, which is a function of the coefficient of pressure for passive condition Kp. So obviously the lateral pressure is Kp gamma z, and as you go to the bottom, it will be Kp gamma into L. But one other interesting thing is all lateral pressures are plane strain problems, which means the wall is continuous. Whereas in the case of pile, it's a 3-dimensional problem. It's a thin member, so the failure surface can go around the pile too. So they found out that the lateral pressure can be 3 times the passive pressure. So we take 3 times Kp gamma z, and this is what happens. You multiply with the diameter to get the force, and we again do a analysis to get you the capacity of the pile. And here I want you to notice everywhere we are showing a certain eccentricity E. The lateral force acting on the structure could be much above the pile, and that's what we need to look into. And so this is how the bending moment diagram looks like, and the maximum bending moment could be somewhere here. If this maximum bending moment reaches the yield moment, we'll end up getting a hinge, and then rest of the analysis is very similar. All I want you to realize is we had to calculate lateral resistance from the soil conditions, Kp being 1 plus sine phi by 1 minus sine phi. You know how to calculate that. If you have restrained head pile in sands, a very similar analysis. You have the pile cap here, the pile is embedded in the cap, and it will be a rigid translation. So H ultimate value is simply equal to area of this triangle. A bending moment is high at the top because that's encased. Then if this starts yielding, you get the first moment, and if it yields at the in between also, you get 2 hinges. So very similar analysis, except we take the passive resistance instead of undrained strength as in case. I think Professor Reddy just now talked in terms of socketed pile. Then we had to look at the different medium. And here you can see the pile is socketed here, and in which case, because the soil above is not very strong, the point of rotation goes into the socket length. If that is so, I had to the reaction from the hard rock here to the left and right. Some of the mechanisms they suggest is, instead of that, we introduce an equivalent force to the left and then continue this reaction here from the right side, and we try to solve by trial and error to find out how much it is. Because to find the exact point of rotation inside a socket length may not be that easy. So something like a sheet pile analysis, we extend here and we try to find out the resistance. And the equilibrium equations are very simple. Sum of the forces should be equal to 0. Moment about any point, rotation about any point can be 0. So 2 equations, I can always solve for 2 unknowns and get the values too. So this is in case of a short pile. In the long pile, this is the one where there's a possibility of a hinge forming 2. So socketing means, please remember, not only the soil, are also trying to get the effect of the pile in the socketed region. So if you do that, we have these design charts which are obtained for most of the cases. Some of these charts are available in our code also. And basically you can find out the ultimate capacity or lateral resistance of a pile. It's normalized with respect to Cu into square of the diameter of the pile on the y-axis, and we have the L by D ratio, length to diameter ratio. And this is for a restrained pile. It basically increases linearly and you get a very high value. You can see that the embedment length of something like even 8 gives me P by CED square is about, whereas for free head pile, it's a function of the eccentricity. If the eccentricity is 0, that means the lateral force is acting at ground level, the curve is somewhere here, and as eccentricity increases, the moment obviously increases and the pile capacity reduces. So if it's a free head pile, the capacity can reduce even at L by D 20 to less than 30 value of the normalized ultimate lateral resistance. I want you to notice something very, very important. When you do the lateral load test, we do a free head pile test, assuming say E by D is equal to 0. You have, let us say, L by D is equal to something like 12. You will end up getting L by D 12. The capacity is around 32 or 33 normalized capacity. But the moment the end cap, you can see the resistance is much higher. So a lateral loaded pile load test, you cannot simply take the value. This is unfortunately one of those strange practices. Many, contractors and some consultants, they do a free head pile load test and give a recommendation that this is the safe load. The safe load from a free head pile load test is much less, much less than the safe load from the restrained head pile. And this is one of the best examples that you can see from very clearly the difference. So this is with respect to ultimate load. The same thing could happen with displacement. So in my practice, I generally look at the deformations or lateral displacement and try to predict based on the actual restraint that I have in the field. And we never go by the free head pile because the free head pile is a very, what should I say, misnomer. We rarely get free head pile except for some pores and maybe in case of a wind turbine with a monopile. The same chart, yield moment is shown here. So if the free head pile, fixed head pile, the yield takes place and yield moment normalized again. You can see the yield moment normalized by Cu into d cube now, and the normalized moment varies from 20, 50, 100, 200. Then the capacity obviously becomes less, but even now with the yield moment, the restrained head pile has higher capacity than a free head pile. So you can use these design charts to get an idea about in terms of the pile capacity for short piles and similarly for long piles too. Whatever we discussed earlier is very true here, and you have a restrained pile much higher than a free head pile with E is equal to 0. I want you to see again, if I was looking at L by D 20, if the pile head is restrained, I get a normalized load of something like 17 to 18. The same thing with a free head pile, I get 10. So that means you have 70% more capacity because the pile is encased in a pile cap. When you come to long piles, again you have very similar result. Only thing is it's a function of plotted here with the yield moment and yield moment by CUD cube against the lateral load ultimate capacity, and for different L by D ratios here and some different eccentricities. And you can see the fixed head one gives you much capacity even with 2 hinges. So please don't go by free head pile capacities too. In cohesionless soil, we make a slightly different analysis in terms of passive pressure, and we get charts are very similar, except the magnitudes are very different in this case. Again, I want you to look at this simple case, L by D 8. If I have a free head pile, I get a normalized ultimate load, which is here ultimate load by Kp diameter cube into gamma against L by D. If I look at 8, I get less than 40, that's maybe around 38 or 35. If I restrain the pile, I'll get something like 80, 90 to 90, which means even a short pile will have something like 2 to 3 times more capacity, and the longer you go, the gap is much higher. So the most practical situation is you have a restraint at the top and free head is very uncommon. Then you combine the yield moment here and you have very similar chart as L by D increases, and if the yield forms, the yield moment is reducing the ultimate capacity, but it is still higher than a free head pile with E is equal to 0, no eccentric load. For long piles, we again have similar results. Only thing is here the difference becomes much smaller. As you can see, the P by capacity by Kp dq gamma against yield moment. So if I have, let's say, E by D is equal to 0, ultimate resistance moment is 10. Yeah, you can see here there's a 20 to 30% more capacity due to the restraint. Similar one for long piles with 2 hinges. We again get the big difference between a free head pile and a fixed head pile. People keep asking, the capacity is low. I know 2 projects where the piles were long and strong, but soil at the top was very, very weak. And because the soil is very weak, CU was very small, we are getting a lot of very small lateral capacities. Well, how can we increase it? So one different alternatives would be, suppose you put in a fill, gravel fill, etc. as a surcharge, you can increase the soil here and the capacity is increasing. Or you can provide the wings. 1 or 2 projects I know in China where they had provided wings on the pile so that these wings will try to take care of the resistance extra. Third alternative would be you provide a collar or increase the diameter of the pile near the top. So instead of taking a smaller diameter, you take a higher one. Because it's CU by D square, you get higher capacity. This is one of the practical situations where you find the capacity is less, so you excavate a trench, fill it with concrete. This is another idea, but I don't think it's very feasible. You can't provide lateral restraint at the bottom. The third one, the last one, is a good alternative. I have 1 pile, and if I know the direction of the lateral force, this is possible in one of where we know the lateral force is acting to the right and the moment is acting there. So we could provide short piles to prevent the top of the pile moving. But in many cases, you cannot fix the direction of lateral force. Then you have to do it all over. That is with regard to the ultimate capacity. We'll now look at the possible variations or how to find the displacements. The most common and the most simple analysis is we treat the soil or the pile soil interaction as a simple Winkler model. I think all of you know a Winkler model is nothing but a spring, and the force in the spring is equal to the displacement. What we slightly modify is that we provide the Winkler spring with a slider, which means it's allowed to there's a maximum force it can take. After that, it will start moving, which means it is yielding, or the maximum pressure is constant. So this is called the modified Winkler model, wherein the soil reaction is linearly proportional to displacement till it reaches the maximum lateral force or lateral pressure. After that, it will be sliding. So once you do that, you can easily analyze and get the response displacement at various loads too. And how do we do that? One alternative would be, we can say the soil resistance is not a straight line anymore. It's a sort of hyperbola. And this is the maximum soil resistance the pile can offer. It's say 9 Cu if you want to put in. Then you can say as the displacement is increasing, instead of taking the tangent modulus, you take the secant modulus. So that way I can take the nonlinearity into account till I reach the ultimate load, but I'm looking at only in the working load range. So I can say, based on, I estimate displacement with a certain tangent modulus. Once I get the displacement, I go to the curve, I get the secant modulus, I put this E value, and we found that in case of sands, the E is increasing with depth. The possible variations are a linear one, or it can increase sort of parabolically and reach kind of very high value here, or it can increase with n is equal to 2. So most common, I would say, is n is equal to 1. We look at the E increasing with the distance or depth from the surface. So once you do that, this is how it looks like. I want you to see the nonlinearity. You have a pile subjected to lateral force and moment. The displacement at the top is very high. So I'm looking at the soil reaction curve, PY curve as they call it. If the displacement is large, the secant modulus is smaller. As you go deeper, the displacement is less, so the modulus is small, less than EP1. And as you go deeper, it's even better. I also want you to realize these curves are becoming much steeper because the capacity of the soil to offer resistance increases. So please remember, this is the kind of nonlinearity you have to look into. The soil at depth is stronger and stiffer compared to the soil at the top, and it's possible to include all of them in our analysis. So at shallow depth, the slope is smaller, ultimate load is less, intermediate value, and you get very high value here too. So we need this value of subgrade modulus KH. We try to find out from plate load test. We try to convert it from here. And if you have, this is one of the standard ones. If I determine E corresponding to 50% strain, I can calculate KH. If you have undrained strength, C of the soil, another correlation says 80 to 320 times Cu by D gives me the subgrade modulus. So if you want some average value, you take 200, something like this. Okay, and here are the charts that I could get from some of the publications, which Tazagi gave in 1955. You have undrained shear strength, stiff soil, very stiff soil, hard soil. The range of K is something like, let's say, 50 to 100, 100, 200, and more than 1. So he recommends proposed value, which is about half of these. So you take some of these if you don't design it, but if you can have some reliable charts, you can always go for this one. You can see for sands, NH values are given by a large number of researchers for different types of soil. For normally consolidated soil, the value can vary from 0.6 to 12.7. For thus, this is the value, and here I have, based on relative density, I have NH meganewton per meter cube for different values. As you can see, the NH value above the water table is much higher than the NH. The rate of increase of Ks with depth is NH, is smaller if you have water table effect. So if I have an intermediate to medium density around 50, NH can be around 15 to 17 below the water table, and above the water table could be 27 to 30. So then once you have those values, we can predict the displacement. You have found out KH, you know the length of the pile, this H is the lateral load you're going to provide, E is the eccentricity. So I can calculate the displacement here. Here you can see these values are given in terms of beta L, which is a short rigid pile less than 1.5, and I can get the lateral displacement, a very simple equation. You also get the rotation here. Theta is the rotation of the pile at the top, 6 times H into 1 plus T, 2 times E eccentricity into L by KLDL square. So you can easily find out these values. And beta, as I said, you calculate as modulus of subgrade reaction T by 4EI to the power of 1/4. Okay, so a rigid pile, in a short pile, in the long pile, this fixed head 1, you can easily calculate the displacement. These are all available in any book and or restraint, these kind of things too. Charts, books and code also. And if you have finite length pile, you calculate beta L. As I said, we look at something like 1.5 to 2.53. Otherwise, it becomes very large. So I want you to again see if the pile is restrained, the displacement is smaller than a free head pile. Here we are getting the displacement coefficient in terms of load, and you find the displacement is maybe half or even less than that of a free head pile. So never extrapolate directly from free head to fixed head. Go through one of these charts and then find out what is the effect of restraint. In case of sands, we have this simple equation, displacement is equal to PL beta into this value, and here is the dimensional Hughes coefficient, and we can take in terms of eta into L. Now eta is slightly different from our earlier definition of beta. It is rate of increase of subgrade modulus with depth by EI to the power of 1/5, and if I multiply that by L, I get the coefficient. It varies from, let's say, 2 to 10, then you get the dimensionless coefficient. Obviously, as length increases, you find the deflection becomes much smaller because the soil is becoming stronger and stiffer. Again, I want you to see a restrained pile gives me very small displacement compared to a free head pile. So these are some of the more charts which are given based on analysis, and they find what is called the critical length. Another alternative would be you find a critical length which is a function of very similar to our beta but slightly different, and based on that you can predict the lateral displacement and rotation due to both force and moment. This is for non-homogeneous soil. Then Poulos at Sydney University, he came out with a continuum approach. Instead of treating the soil as a Winkler medium, we are treating the soil as an elastic continuum with ES as the modulus of deformation, and the coefficient Kr is a relative flexibility parameter. EP/IP is the flexural stiffness divided by ES into L4, and that gives me Kr. And then he said the displacement is a function of load, H2, rotation due to horizontal, displacement due to horizontal force, and this is due to moment. Similarly, you can get rotation in terms of horizontal force and the moment. He has given a series of these charts which are available in his book. We can download from the internet too. So as a function of Kr. Kr is 10 to the power of -6, very flexible pile, and Kr more than 10 to the power of -1, it becomes a rigid pile, and the displacements are almost constant. So as a function of L by D and the relative stiffness factor, I can get displacement. Once I have I rho H, I can simply substitute here H by ES into L into I rho H will give me displacement due to horizontal force. If I know I rho M, as you can see in one of these charts, here is the relative flexibility parameter Kr and L by D. I can get the I rho M, go back here and calculate the displacement due to moment. So very simple design charts which are available in all these cases. Similar to what we have seen earlier, we have a fixed head floating pile, and we have relative flexibility factor, Kr, and the I rho h, you can substitute there and get the displacement. And you will find once again the displacement due to fixed D at the top will be much smaller. This is the for sands where modulus of deformation ES is increasing linearly with depth. And in this case, we define the relative flexibility parameter as EPIP into NH. Earlier we had E into L4, but now we get rate of increase of E with depth, which is NH into L5, and you again get in terms of Kn and the parameter I rho h for sands or where the soil E increases with depth. This is for I rho h, I rho m, and this is I theta m, the moment rotation due to moment. If you socket it, it makes a big difference. You'll get another set of curves here, and you'll have to take those parameters. I just wanted to show you what could happen if you have an earthquake. The problem is people think that piles are good for seismic resistance, but it's not necessarily true. What could happen is in this particular case, as you can see, you have an earthquake, you have building with piles. Because of the moment the soil got liquefied and the resistance is gone, they ended up getting a crack or pile has sheared here at the interface between the reclaimed fill and original sand layer, and so the building has got damaged completely. So what I want to show here or say here is that piles are not a simple solution for earthquake resistance. You have to look for alternate ways of improving the ground rather than providing piles alone. These are the different mechanisms we consider with pile mechanism. With piles for the support, okay, this is a typical pile with pile foundation. There could be a shear failure, or you can end up bending failure here. This is a buckling kind of mechanism, and this is what you call dynamic amplification. As you go top to the higher level, the earthquake force gets multiplied. So all these are complex mechanisms you have to consider. So when you design for liquefaction, you have to assume that this layer is not going to contribute anything in terms of lateral resistance. Initially, as you can see, the N values here in the top sand, clay sand, N values were less than 10 up to this depth. Then we have a fine sand layer, silty layer. Even here, the N values were less than 20. So when we did the seismic analysis, you find the factor of safety is less than 1 in this zone. So we assume that it's likely to get liquefied. Once it is liquefied, the reaction from the lateral capacity to the pile will be 0, and that's what you have to consider there. So the pile may end up getting a large displacement. It can also, if you restrain at the top, it may kind of hinge at the bottom, and you'll get a large displacement at the center, or you'll end up getting these kind of loadings in these cases. Okay, when you have cyclic loading, you have a similar problem or much more complicated. If the pile can move along with it, fine, but if the pile is restrained, because the inertial force, you will get a lot of resistance here. Okay, so people talk in terms of liquefaction potential index. We had to calculate based on these parameters. How is the factor safety against liquefaction at different depths? What is the in terms of the displacement with the depth, and you calculate the liquefaction potential index as a function of depth and the factor of safety against liquefaction. Only when you have low values of LPI, otherwise you will end up getting higher liquefaction into. So based on that, if N is equal to less than 8, you can see the chance of liquefaction are very high, and you have to reduce the modulus, whatever is the static value, to less than even 10%, you can see it's hardly 5%, which means there is hardly any resistance. Whereas for higher values of liquefaction, I mean, the smaller values of this, you can get much higher one too. These are n is equal to 14 to 20, and these values are for. So wherever you end up getting SPT-N less than 8 or 10, be sure it's likely to get liquefied, so piles may not be a good solution. And I just want to show you one particular design. They were suggesting for earthquake, a board cast in situ piles. We were recommending them that you try to improve the ground first with stone columns. And then we also said that it will be good in terms of carbon footprint. So we just compared, this is for Delhi Metro, board cast in situ piles. The carbon footprint because of concrete is so much, 667,516 kg. The reason is, I think you know, when you want to manufacture cement, 1 ton of cement requires 1.5 tons of carbon dioxide releasing. 1 ton of steel probably generates 2 tons of carbon dioxide. So when I look at the typical project, if I use board cast in situ piles, you're generating about 1,250 tons of carbon dioxide. Whereas if I improve the ground, I only use about 161 tons of carbon dioxide, because when I'm breaking stone, I need a lot of energy and I need to transport it during installation, etc. So we go for recommending that in case of liquefaction, piles are not the solution, ground improvement is the best one. And how do we do that? We know the sands are in loose condition, which means one grain is sitting on top of another. That's how you get the loose one with high void ratio. If you can vibrate it with something, you can rearrange the particles so that the particles sit in the valleys of the adjacent lower one, and you reduce the void space, you increase the number of contacts, and becomes very dense. So, I'm sorry, God. Can you hear me now? Hello?
Yes, sir, you're audible. Sir.
You're audible, sir.
Okay, so what we do now is that we try to densify the ground by vibrocompaction, and the simple mechanism would be you introduce the vibrofloat, compact it, and add material to finish it to complete this thing. We found out this is a very good alternative. Some case studies we are in a Punjab area power plant. You can see the N values before densification are very less. This is stored static cone. After densification, larger one. So it's better to treat the ground rather than go for pile foundation. Another case is a building in Noida where you had very low N values, and after densification, you have more than 20. And another way they tested was do a simple plate load test. And even if you put something like 30 tons per meter square, the plate gave hardly 4 to 5 millimeter settlement. So the effect of densification you can see here. Packaging unit in UP, you can see the initial SPT and the densified value here, which is, if you can increase the N value beyond 20, the chances of liquefaction are 0. So my suggestion is, if you have a seismic one, don't go for piles, go for densification of the ground, then introduce your piles if necessary. The main thing I want to show is that from here onward is the capacity of the pile depends on the displacement, or the allowable load that you can put is a function of displacement, and we should not go for those ultimate design values. So one of our colleagues here, Professor Padmavati at JNTU, worked a lot on this. She was studying the response of a pile due to lateral force and moment using Winkler, except that we were looking at a hyperbolic response, which means the lateral stress is increasing with displacement, and the way it is linear is what earlier we are looking at. The lateral response is subgrade modulus into rho, but instead of that, you take it as a hyperbolic response wherein the lateral resistance Q is equal to Ks into rho, the lateral displacement, 1 plus Ks into rho by Q max. So as you increase the displacement, the pressures decrease, and this is how the response looks like. So she was trying to analyze this using a simple mechanism as we see here, a short rigid pile, and you can see the displacements are maximum here, decreases to 0, increases on the negative side here linearly below. So if I know the displacement profile with a rigid pile, I can substitute here and get the value of Q and integrate it. Very simple mechanism, and we can also find out the point of rotation from equilibrium equation, and this is what she did. Okay, in case of cohesionless soils, we considered Ks increasing with depth, and of course the ultimate value too. And in this case, as you can see, the parameter what we called as NH is nothing but T to the power of 1 by 5. So what we're trying to look at various alternatives. If you remember, Brahms was suggesting that ultimate load, this is of course given by Hansen, Brahms, then one of these Polish mechanisms, Meyerhoff, then we had Prasad and Chari, which is from Newfoundland, and the resistance variation, different forms were considered, and we were looking at various alternatives in terms of Ks and Q max variation with depth. Ks is increasing with depth with a rate of alpha K. The ultimate resistance is also increasing with alpha Q. And so you can write those equations very simply based on this pressure distribution. So, she did a lot of parameter analysis. We looked at again the rate of increase of dry moist sand, which is above water table, below water table. Obviously, this below water table will be much less compared to above water table. This is taken from Terzaghi. She worked for different lengths of pile, 3 to 30 meters, pile diameter 0.3 to 6 meters. It's of course very high. Angle of shear resistance of the soil is 25 to 50 degrees. Unit weight of the soil varies from 16 to 21. So we convert that into relative stiffness factor, pile rotation theta, and normalize eccentricity. And these are the curves. I want you to look at the variation of load with displacement. So which means you don't have to go to the ultimate value. You can work at different levels. Mu is nothing but subgrade modulus into L by Q max. If Q max is very large, obviously mu will be 0 and you will get a linear behavior. But I can calculate based on the subgrade modulus for various displacement, or if I know the load, I can get the displacement here. So for first, we are able to predict the displacement for a given load, or for a given displacement, what is the load, using both Ks and Q max. So this actually depends on how the pile is behaving. And how do I get the ultimate load? When I have pile load tests, I use the Corners plot, which is hyperbolic 1. Displacement by H is plotted against displacement, take the slope, inverse of the slope gives me the ultimate load. So I've been able to estimate these and now predict even the point of rotation. So as mu increases, the point of rotation goes deep below for different loads too. It is not a constant, it varies with depth. So this is something I would like you to see, and these are how the pressures are mobilized. I want you to see the difference between these pressures and Brahms are assumed, that is for ultimate load, and you can see the pressures here could be very small at the top because soil is very weak, and then you get much higher. This is what I would look at as a design chart for different eccentricities. E by L is equal to 0, no eccentricity. So displacement versus load, you get a continuous value. So if you know the displacement, or if you know the load and eccentricity, you can get the displacement. Either way, it is the same. Okay, now we are comparing the predictions. You can see here in terms of bronze has given you a very high value, but because of the non-linearity, you get slightly less for different L by D. Prasad and Chari and Zhang, they had a different model, because of which they're under predicting compared to the values we got here too. So when I look at the kinematics, how the soil pile soil reaction looks like, here is the design chart for different L by D and different eccentricity. You get the ultimate load, which is a function of both eccentricity and L by D. And then we are also looking at the comparison between predictions and the ultimate values. This is a very interesting one where we found out different mechanisms and different values, how people are predicting. And I would like you to see, compared to the observed and the measured values, there's huge, sometimes very significant difference. Okay. And you find that this is a measured HU versus, and initially for small values, no problem, but these are all lab experiments, so you can see small load. But once you go higher, you find the values are very high. According to Dr. Padmas's work, you can see her predictions are all falling on the 45-degree line, which means if you look at the kinematics, you can predict better. And we also try to compare in terms of the load displacement relation. And you can see here, the actual observed values are the points, and theoretical value is given here, where we didn't know exact value resistance, but because these are all very small model scales, we scaled the angle of shearing resistance and we were able to measure better values. Here is another case we got from Mehrhoff data, and we find that the fit is much better. So when you look at the lateral load capacity, the kinematics is very important. Why we say that? Because you can see under high stress, I mean, the Moore envelope for sands is highly nonlinear, and you should not take a simple linear relation. We find that it can be a curve, and that is why we include that. This is what we were looking at in terms of as a function of vertical stress. At low vertical stresses, you will have higher shearing resistance, and at larger ones. So when you interpret your lab test, don't go for direct shear test result, go for a low value shear angle of shearing resistance for a low normal stress. And this is what was happening. This is another interesting data we have. This, of course, load displacement, which is matching. These are other lateral pressures which are measured by Radhakrishnan 73. We had this data. The measured values are the point, and the ones that is predicted by Padmati is around 5. You can see it's much better, much closer to compared to earlier predictions. Another one prediction you can see the prediction using Padmati's data is much closer to the measured values. These are the reactions that people have assumed. Brahms neglects here. McDonald says, you go 3D, but don't neglect at the top. This is the undrained strength at the top is equal to unconfined compressed strength. You go 3 times diameter, you get 9 CUD. And the present approach is where we are assuming a gradual variation rather than step function. Okay, and this is how we are able to estimate the lateral capacity. So here, the bronze predictions are here, and the McDonald one, whereas ours are a function of this parameter mu, which is your Ks into D by ultimate resistance. So instead of just looking at only the ultimate resistance, the stiffness also is very important. Different comparison, and now we can see that because we are able to consider the both stiffness and the ultimate resistance, the predictions are much better. The measured values are shown here and the predicted, they match. So what I would like to finally recommend is, this is another good comparison. Brahms and McDonald, they give the step function, whereas if you take the kinematic, you're able to predict the variation of the depth. Okay, and this is how it improves. Similar what she did for both the layered soil too, and we have a lot of data based on that. You can do for different combinations. This is another good fit that we had, experimental and proposed the match. Two layered coarser soil. You have one type of soil above, another type below, and she did a lot of parametric. You have a softer soil overlaying stiffer one, and stiffer layer over the soft one too. You are able to generate these parameters and get your variation of lateral pressure with depth. And this is your load versus displacement for different combinations of layer thicknesses and layer stiffnesses. You get many of these charts wherein you find the ultimate lateral load as a function of relative because of layered soil. Okay. And we were able to compare with some results which are available with Poulos. He said there is a dead zone, whereas we have a continuous profile too. The way Poulos looked at is a step jump, whereas ours would be a gradual variation because of kinematic. So these are some of the comparisons. One particular example where we had a two-layered soil. Actually, it's a little more complicated, but we converted it to a two-layered soil, and where we have been able to predict and then measured very closely with this proposed theory. When you have pile growth, Poulos again came with a very interesting analysis. If you have a pile here, another pile adjacent to it, the interaction depends on whether the adjacent pile is in front or away from there. So I want you to look at this angle theta. If theta is 0, the second pile is in the front, and if theta is 90 degrees, the second pile is orthogonal to it. So the influence varies as a function of whether a function of theta, and you can see it depends on angle theta, and in front gives you maximum interaction and least when you have orthogonal one. And he calculated the displacement caused by the adjacent pile due to the load. So it increases by about, depends on the spacing, and you get different values. If you have a close spacing of 2, you have very high interaction, and if close spacing is 5, it's much less. These are the interaction factors for various conditions he has given. So we can analyze pile groups based on this value. And then based on that, he finally came out with the group reduction factor, wherein what will be the settlement of the group relative to that of a single pile with a single one. So for 2 square, 3 square, etc., we have a design chart wherein I can say by providing number of piles, how much can I reduce the settlement. So these are some of the chart for different spacings. The larger the spacing, the better it is, but then the cost goes up. Again, you have the fixed head pile and the free head pile. And so you can see that again, a function of the pile fixity. The more interesting thing would be, how are these loads affected depending on their location? So you can see if I have the corner piles, this is a 3 pile group, 4 corner piles, and the two intermediate, and then one at the center. And the load on that will be a function of spacing. The group in me, which means that not all of them will carry the same load. And lastly, I would like to come back to the effect of soil movement. So here is how we look at it. If you have an embankment which you need to stabilize, and if you put the stone columns or piles here, the load from the embankment will come on this way. And if you have a tunnel which is being created, you don't want the movement due to tunnel construction. You want to predict the ground, you provide piles too. This is for piles for slope stabilization. Sometimes pile driving itself may give rise to problem, or pile adjacent to an excavation. You already have a pile, and if you make an excavation, the soil movement will cause the piles to move. So these are some of the challenging problems you have. I would like to end with showing some nice picture of a natural forest wherein we don't know why all the trees have taken this shape. Then another pun for today. I used to hate math, but then I must have a point. I would like to end my presentation with my signature. Geotechnical engineering is a science, but it's practice and art. So what we tried to cover today would be how to analyze piles subjected to lateral forces and moments. And in nutshell, you have to consider 3 to 4 parameters. One is L by D, which will tell you whether it's a short pile, intermediate pile, or a long pile. Second would be the pile fixity at the top and at the bottom. At the top, it can be free or fixed inside a pile cap. At the bottom, it can be free in case of a floating pile. It can be hinged if you drive it into hard rock, but not much. So lateral displacement is restrained, but more rotation is allowed. If you socket it into hard rock, it becomes a fixed pile. The analysis are either based on ultimate capacity, or if using Winkler, you are using only subgrade modulus. What we now covered would be kinematics, in which case we also look at both the ultimate lateral resistance of the pile and the modulus of subgrade reaction, but look at it as a hyperbolic response and try to find out what will be the ultimate capacities and what will be the design displacement. We can also look at how layering effect. So if I have a soft layer on top compared to a stiff layer, or if you have a stiff layer on top and a soft layer below, you can find it out. Thank you very much. And I would like to now share any of your comments that you may have. I'd like to listen to you if you have any point that you would like to discuss. It's a very interesting field, but you need a lot more data to predict the behavior. And my recommendation is don't treat the pile as free head. Always look at a fixed head pile and see what kind of restraint will give you in terms of performance.
Hello, sir.
Yes? Hello? Yeah. Can you wait a minute? Yeah, can you?
Yes, sir. For suppose if the constructor client has given the lateral load capacity by conducting the free head, and if they are going to do pile capping and all, in such cases, can we increase the capacity by 30 to 40% and recommend it, or what should we do?
That 30 to 40 is something which I will not be able to precisely tell, but I'll go back to my analysis, and if for a given L by D and for whatever condition, I get a capacity and I look at the chart. I've given you some of the charts. Use the chart. It can be even more than 50 to 100%. My point is 30 to 40% is very safe, but actually it could be even much more depending on the geometry of the pile and the ground conditions. One of these charts, you have L by D, you know free head pile, and you also have fixed head pile.
Yes, sir.
Use that chart and say I can increase it in terms of ultimate capacity. Then you also go to the one in which I showed you the displacements. There again, you will find that fixed head will give you much smaller displacement than the free head, so I can reduce it too. You know, my point again is, let me tell you, ultimate capacity is a one extreme case. Most of the time, we are interested in the serviceability limit condition, how much displacement can I allow. When you do the code, they say 5 mm is the lateral displacement. You know, at 5 mm, what is the load? That is considered as the ultimate load for free head pile. But for a fixed head pile, if I look at displacement, as you said, it can be more than 30 to 40% or even 100%. So instead of, you know, taking a vague value of 30 to 40, I suggest you go for one of the design charts, use that to increase the lateral capacity for design. Okay.
And in that clay soil, sir, initially you have mentioned that 9 times CU, the undrained shear strength.
Yeah.
Is it an empirical value or any background is there in that?
There's no background. Just that Brahms has given that it can vary anywhere from 12 to even 9 to 12 or 16 also.
Okay.
But that is some arbitrary value.
And that alternatives which you have suggested, which was shown, no, sir, that what do you mean by these wings which was provided at the top?
It means you provide a blade kind of a thing. But what I would like you to do would be actually, which is what I would recommend, I take now the lateral capacity of the pile cap. One of the projects I had, the pile cap was around 3 meters below the ground level, and the pile cap thickness is around 2.5 to 3 meters. Okay, so then we were treating it's extremely soft variant clay, so we replaced some of the top layer with a good granular material. So I have a pile cap with piles. The piles were giving me hardly 2 to 3 tons per pile, whereas the lateral capacity for this power plant were much higher, lateral forces. Then what we said was the pile cap is very large. Let's say it's something like 8 meters by 8 meters or something, and the thickness is 2 meters at a depth of 3 meters from ground level. So when I look at the passive resistance, the pile cap will move with the piles, right?
Yes, sir.
Why should I only take the pile capacity alone? I can take the capacity of the pile along with that of the pile cap. Then I could increase the capacity and get values. So what basically is that you can think in terms of the pile head damaged, or pile head size is increased, or pile group size is increased. Okay, that is one way you can.
Sir, can you suggest any textbooks for understanding this lateral load capacity?
The two very good books are Poulos and Davis, Pile Foundation Analysis and Design, which is available if you go to International Society website, you will get it. Another very good book, 3 books actually. Tomlinson is good, for Deep Foundation, Shallow Foundation. Third one is by Fleming, and one more author is Randolph. Piling Engineering is the name of the book.
Okay, sir. Thank you.
Thank you. You're welcome. Any more?
So any more participants would like to interact? They can interact. Sir, I think you have answered
Okay.
Shaker's question for lateral load capacity of group pile. Any method available in IS code or other methods?
But only thing is, be careful. IS code is very, very misleading. I've been trying to change it to look into the fixed T conditions. And don't use your data from freehead pile at all, unless you modify it. Okay? Have a good day. Thank you very much. Thanks, Professor Reddy.
Sir, thank you very much, sir, for sparing your time and delivering lectures on the topics of static load tests on piles yesterday, and for covering the important topic of lateral load carrying capacity of piles. So we look forward for your 2 more lectures in this FDP. One is on 28th on new perspectives on bearing capacity, and again on 30th one more lecture on the topic of engineering of ground for foundation on weak or soft soils.
Yeah, sure. Okay.
Thank you very much, sir. Okay, sir. I thank all the participants for their active participation. So try to join in time. So make your time free so that we can start these sessions in time. Hope you are enjoying the sessions. Right, go through the missed content if any due to your other schedules if you are missing. Later on, spend some time, watch YouTube, right? Through YouTube, you try to watch the lecture once again. If you have any clarification or query, you are free to discuss, right, at the end of any session. So I thank you all, right, for your participation and interest, right, in upgrading your knowledge. Because by attending to your regular work, right, you are finding out time in the morning and evening and attending all the sessions. So thank you very much. Have a good day. We'll again meet at 4 o'clock for the lecture on dynamic pile load test on piles and NDT testing of piles, right? You might have heard of pile integrated tests, right? Which the tests are used in quality control, right? Evaluation of casted piles. So the evening session will be engaged by Sri Ravikiran Vaidya of Geodynamics, Vadodara, right? So that's all for now. Have a good day. So before leaving, right, kindly submit the attendance sheet